Okay, so let's get started. So last time we sort of started chapter 3. So we're looking at linear programming. So last time we just looked at linear inequalities, and now we're gonna do something called linear programming. So a linear programming problem consists of, so first of all, a system of linear inequalities. Okay, so that's the kind of thing we looked at the end of last class. And these linear inequalities are called constraints. And a linear function called the objective function. Okay. And when you're given a linear programming problem, your goal, so we'll see an example of this in a minute. I know this is a bit kind of abstract to just kind of explain it like this. But generally, the goal is to find the maximum or minimum value of the objective function over all choices of the variables that satisfy the constraints. Okay. So writing this all out in words, it all just sounds a bit abstract. It's maybe not clear what I'm talking about. But I think it becomes clearer if we see an example. So we could be asked to maximize, let's say, 3x plus y. This would be our objective function. So if we're asked to maximize something, that's probably the objective function. We could be asked to minimize it as well. And then I'm going to say, so subject to the constraints, that x plus y is at most 1, 4x plus y is at most 2, x is at least 0, and y is at least 0. So these things would be our constraints. So right, when I say that we're dealing with like a linear objective function and linear constraints, all I mean is that this is a linear function of x and y, meaning it's just like some constant times x plus some constant times y, and there's no like, you're never going to see any kind of x squared or anything like that, right? It's just x's and y's with the power like 1, the exponent 1, right? Okay. So is it clear what this is saying? So this is saying out of all the possible choices of x and y that satisfy these 4 constraints, so out of all of those possible choices for x and y, we want to make this function as big as possible. Okay. So there's a sort of step-by-step method for solving these things. So step 1, and this is in general, if you're ever given a linear programming problem, this should be your first step. You want to graph the feasible region of the constraints. Okay, and this is what we did at the end of last class, this kind of thing. So yeah, I want to graph this region. What I'm first going to do is I'm going to find the line x plus y equals 1. So to do that, I think the best way to do it is to look at the intercepts. So if I put x equals 0, I get y equals 1. So I know that this line goes through the point like 0, 1. If I put y equals 0, I get x equals 1. So it goes through the point 1, 0. And once I know 2 points on a line, I can just draw the line. So this is the line x plus y equals 1. Okay. For this line here, if I put in x equals 0, I get y equals 2. So that's up here somewhere. If I put y equals 0, I get x equals a half. So here I'm trying to draw the line 4x plus y equals 2, right? And yeah, so it should be this kind of steep line. Okay. And then the line x equals 0 is just this vertical line. Y equals 0 is this horizontal line. Okay, now I need to find the feasible region. So I need to kind of like shade something. So, okay, so this here is the line for x plus y equals 2, right? This line. So, okay. So now for each of these lines, let's say I take the line x plus y equals 1. Which side of this line, above or below, is like the feasible side? So I'm supposed to be finding x plus y at most 1. Yeah. Yeah, exactly, yeah. So like to check which side is the correct side of the line. You just have to plug in one value that's not on the line. So if I plug in 0, 0, I get 0 plus 0 is less than or equal to 1. So we should be kind of shading this side of this line. So I'll just draw some arrows at first. Similarly, for this line, for 4x plus y equals 2, for that line, the correct side is below the line because it's, if I put in 0, I get 0. 0 is less than or equal to 2. That's true. So I get this side. And then x at least 0 is over here. Y at least 0 is above here. So at the end of the day, that's my feasible region. Okay. So this is the set of all x, y that satisfy all 4 of these constraints. Any question about that part? Because this is kind of important. Okay. Now, okay, this is fine. I've got this graph, but the next thing I need to do, my second step of my process for getting a solution, is to find the corner points or I think your textbook calls them vertices of the feasible region. Right, because you can see that this region, it makes kind of some sort of shape in the plane, right? And that shape has some corners, and we need to know what they are. It might not be clear yet why we're finding these corners, but in a few minutes I'll tell you why they're important. So we already know 3 of the corners, right? This is the point 0, 1. This is obviously 0, 0. And this we already found out was 1/2, 0. Right? But this corner point here we haven't found, so we need to figure out what that is. By the way, what really defines a corner? Like, a corner of the region is any point that is on 2 of the different boundary lines of the region. Right, so this one is on the line x plus y equals 1, and it's on the line 4x plus y equals 2. So yeah, we need to find the coordinates of that point. Is everybody with me, or? Here's one cool thing. We can use stuff we've already done in this course. Because I want to find a point I want to find some xy that is on the line x plus y equals 1 and the line 4x plus y equals 2. Because that will give me this point. That's the only point that's on both of the lines. But this is just a system of 2 equations, right? I want x and y to satisfy this equation and satisfy this equation. So we can do this as a kind of Gauss-Jordan thing. I can say 1, 1, 1, 4, 1, 2, right? I want x plus y to equal 1, and I want 4x plus y to equal 2. Is everybody with me how I got this, this thing? I wanted to solve these two equations at the same time. Right, now I take my row 2 minus 4 row 1. Right. Row 2 times negative 1 over 3. And there's just not quite enough space here for this last step. I'll just write it over here. But row 1 minus row 2 would give you 1, 0, 1/3, 0, 1, 2/3. Right, so this tells us that the correct point is x equals 1/3, y equals 2/3. And as usual with these things, if you're not confident about the solution, you can always plug it into your equations here. So 1/3 plus 2/3 is equal to 1. That's good. 4 times 1/3 is 4/3, plus 2/3 would be 6/3, which is 2. So you're good, right? So these are the coordinates of that point. So this is the point 1/3, 2/3. And if this was a more complicated linear program with more and more constraints, you might have a lot of corners on this. Imagine I have another line that cuts through and cuts that off and then cuts that off, and you could have corners all over the place, right? In which case, you may need to solve many of these systems of linear equations. Yeah? Like it's broken into kind of two parts or something? No, I think it's always going to be some connected kind of region like this. Okay, so step 1, graph the feasible region. Step 2, figure out the coordinates of the corner points, which we've done now. And then the last step uses something called the fundamental theorem of linear programming. So this says that if the maximum or minimum of a linear programming problem exists, okay? So if there is a maximum or a minimum, then it's always achieved at one of the corners of the feasible region. So it's always achieved by one of the corners of the feasible region of the constraints. So just to kind of apply this in this problem, or maybe to just sort of rewind and kind of say what we're trying to do. So these are the points in this region are all the feasible x's and y's, or xy kind of pairs. So these are the feasible choices of the variables. We want to make this function as big as possible over all choices of x and y in this little box thing. And the amazing thing about this fundamental theorem of linear programming is that it says that you don't have to try some point in the middle of this box. Like that can never be better than checking the corners. So basically, if I want to maximize this function 3x plus y over all the points in this region, well, it's enough to just check these 4 corners and take the biggest value out of those 4 corners. So you don't really have to check all of these infinitely many different options. The corners are good enough. So the third step in this process is just evaluate the objective function at the corners and take the biggest or the smallest value, depending on if you're trying to maximize or minimize. So take the maximum or minimum value. Okay. So literally, all we have to do to finish this problem is plug in these values into our objective function, which was 3x plus y. So if I try 0, 0, maybe I'll put this in a bit of a table or something. My objective function would be 3 times 0 plus 0, which is 0. So I'm just plugging it into this function here, which is the one we're supposed to maximize. I'll try another corner. So I'm just trying the 4 corners on that picture over there. One of them was 0, 1, which is going to give me 3 times 0 plus 1, which is 1. 1/2, 0 will give me 3 times 1/2 plus 0, which is 3/2, 3 over 2. Then if I plug in 1/3, 2/3, I get 3 times 1/3 plus 2/3, which is 5 over 3. And if you check, this is a little bit bigger than that. So this is the solution. This is the answer. Okay, because this is out of these 4 values, these 4 corner values, this is the biggest. And the biggest value always has to be achieved at the corners, so this is good enough. Okay, this is, yeah. Okay. I kind of did that a bit quick, so are there any questions about that? So really, you just want to follow those 3 steps, right? Graph the feasible region, find all the corner points, and then plug all the corner points into your objective, and pick whatever's the best value. Yep. Yeah, so that's just graphing these four lines, like, well, the line x plus y equals 1, which is that, 4x plus y at most 2, or equals to 2, which is that, x at least 0, y at least 0. And then you have to determine for each line which side of the line is it talking about. And you do that just by plugging in values. So if I plug in 0, 0, I get 0 as at most 1. So this one, we should shade the side of the line that contains 0, 0. And yeah, then you can get your feasible region eventually. I'm not sure if that helped or not, but yeah, that's important. You need to be able to get this feasible region. So you want to practice with that. I should mention that, like, I think a normal convention is to, so we've been shading the feasible region. You might see some practice questions or even some quiz questions where they tell you to shade like the opposite, like shade the side of the line that's not in the feasible region. You just need to really read the question really carefully to know which side you're supposed to shade. I don't know why they do that in the book, but just watch out for that. Sometimes they'll ask you to shade the part that you're removing to get the feasible region rather than the feasible region itself. So just read the questions very carefully. Okay, by the way, so suppose now this question was asking for the minimum value of that function. So can anyone see what it is? Yeah. Yeah, exactly, 0, right? If they ask for the minimum, we don't have to change anything, right? We just have to change our final answer to be like, okay, it's not this one anymore because that's the maximum. So you should take the minimum over the corner points. Also though, if now you kept the same constraints and you changed your objective function, like let's say I just say, okay, we want the same constraints, but we want to minimize a different, or maximize a different objective function, like 3x minus y. Well, you don't have to redo all this work, right? Because this didn't depend on the objective function. So if it was 3x minus y, you would just plug in these values into that function and take the maximum or the minimum, right? So you don't have to start from scratch. So one thing I just wanted to also mention here, so if you kind of read the wording of this theorem, it's kind of funnily worded, right? Because it says, if the maximum or minimum exists, then it must be at one of the corners. But that kind of suggests that sometimes the maximum or minimum might not even exist, right? Which is true, so you need to be aware of this as well. So some linear programming problems don't have a maximum or maybe a minimum. Okay. And there's kind of two reasons for this. So the first way, or one way that a linear programming problem might not have a solution is if there's just no feasible region at all, right? So the feasible region may be the empty set. Okay. So then obviously I can't maximize the function if there's no choice for the variables. So for example, if I say maximize x minus y subject to x plus y being at least 7 and x plus y being at most 3. And if you think about it, well, how could this be possible? You can't have, a number can't be bigger than 7 and also less than 3, less than or equal to 3. So there, here you would have no, the feasible region S would be the empty set. Okay. So another reason that you may not have a maximum or a minimum is because maybe there is no maximum because the value of the objective function can just be really like as big as you want it to be. So the objective function may be unbounded. Okay, for example, if I wanted to maximize 3x plus y subject to x plus y is at least 1. Well, here we can say there's no maximum because like I can just make x and y really, really large. I make, you know, if I just make x and y both equal to 1 million, then I'll get 4 million. If I make it 1 billion, I get 4 billion. Like there's no limit. And all of those choices will satisfy this inequality, right? So the maximum in this case is kind of, there is no maximum because it's kind of infinity, right? So that's just something to be aware of. It's not true that every problem has a maximum or a minimum, but for all intents and purposes, in this course, probably everything you'll encounter will have a maximum or a minimum, and it'll be attained at one of the corner points. Yeah? You might need to kind of solve it. Like, for example, in this case where you have where the feasible region is empty, when you go to try to graph it, you'll be like, okay, this side of that line, this side of that line. And if you realize, oh, there's nothing that satisfies all the inequalities, then you can say, okay, there's no solution because the feasible region's empty. So when you do that first step of graphing, you might notice it. In this unbounded case, also, I guess you may notice it when you graph it. It's a little bit harder to notice, I think, but you'll see that your feasible region goes off to infinity in some direction, and then you might be able to recognize that, oh, I can just take these values to be really large, and then whatever. But those won't be typical problems that you'll encounter. Usually we're going to have this nice situation where you've got a nice feasible region and you just check the corners. Okay, we'll start kind of working on a word problem here. I don't think we're going to finish, but we can always finish next time. So, okay, so let's say Greg is trying to make a balanced diet. by eating only rice and soybeans. Probably a bit ambitious. So he's only going to eat rice and soybeans. And he notices he needs to eat at least 90 grams of protein per day, 1,620 calories, and 1 milligram of riboflavin or riboflavin. I'm not sure exactly how you pronounce that. Okay. And for whatever reason, he doesn't care about anything else, about like vitamins or other vitamins or minerals or anything. So all he cares about is his protein, his calories, and his riboflavin. So rice contains, so a cup of rice contains 15 grams of protein, 810 calories, and 1/9 of a milligram of riboflavin. Okay, and it costs 21 cents. Okay. These questions have so much information in them, but a cup of soybeans contains 22.5 grams of protein, 270 calories, and 1/3 of a milligram of riboflavin, and it costs 14 cents. Okay. Okay, so the goal is going to be this Greg person wants to get enough protein, enough calories, and enough riboflavin, and he wants to minimize his costs, right? So the goal is to minimize cost while cost of, but subject to having to get at least this much of protein, this much calories, this much the other thing. Okay, and so how much, basically how many cups of rice or soybeans should he eat per day? Okay. So to me, it's not obvious what the answer is, right? Because if he eats a bunch of rice, that's going to give him a lot of calories, right? So he'll easily get to the 1620 calories, but it's going to be hard to get to the right amount of protein and the right amount of this riboflavin and stuff. Whereas eating a lot of soybeans is going to be hard to get the right number of calories. So he probably wants to blend, he put a little bit of one, a little bit of the other. And we have to figure out what's the best amount of each. Also, soybeans is a lot cheaper. So you kind of think you might want to eat a lot of soybeans, but yeah. So here, the first step before doing anything is just going to be to write this down as a linear program. So we've got two unknowns. One unknown is the number of cups of rice. The other is the number of cups of soybean. I guess per day that he buys and eats. And then y is the number of cups of soybean. Okay. So our objective function is going to be the thing we're trying to minimize, which, you know, we want to minimize the cost, right? And so let's do this all in cents. So we want to minimize 21 times x plus 14 times y, because that's your daily cost in cents. Right? Okay. So can anyone think of what the constraints are going to be, or one of them? Yeah. 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 So each of these requirements, right, is going to have a constraint. So, you know, you need to get at least 90 grams of protein. So we should say, okay, how much do I get per cup of rice? It's, I think, 15 or something. So every cup of rice gives me 15 grams of protein. The soybeans gives me 22.5 grams. And that has to be at least 90. So this is my protein constraint. Then we get a similar thing for the others. So I think 810 calories per cup of rice plus 270 per cup of soybean. And that has to be at least 1620. And then we've got 1/9 x, I think it was, yeah, plus 1/3 y is at least 1. And this is for your riboflavin. Okay. So there are actually two other constraints that are not obvious here. Like, it's not really given to you in the question, but in some sense it is. Yeah? Yeah, exactly. You can't go in, like today I can't say I'm eating -1 cups of rice, right? And you also can't buy -1 cups of rice unless you're selling rice, I don't know. But so So these constraints, they're not really given in the question, but it's kind of common sense. You can't eat a -1 cups of rice, right? Right, that's just, you can't, all I've written here is you can't eat a negative amount of something. Okay, so at this point, so this is another skill you're gonna have to have is like reading a word problem, turning it into a linear program. And then from this point forward, everything is the same as before. What you wanna do is you wanna graph your feasible region, you wanna find the corners, you wanna plug those corners into your objective function and take the smallest value that it gives you, right?